Hello and welcome back. So today we're going to be doing part 7 of building an AI computer improviser from scratch using Max. Following up on part 6, which was generative approaches to rhythm. Today we're going to be looking at more reactive approaches to rhythm using Markov chains that will analyze the time differences between onsets in our audio corpus, as well as what the live input is doing. And then pulse and meter detection. Okay, so quick recap of where we're at. So we have all of our analysis objects here. I've, as usual, used the MFCC slices just to sort of have something in our audio corpus that's been analyzed. This is a recording of myself improvising on fretless guitar. We can hear little bits here. So it has sort of a nice tonal quality to it, some pretty clear attacks. And yeah, so it should work well for our testing purposes today. So let's get right into it. So let's make a new subpatcher, and this can be our Markov rhythms. So we'll also use Markov, implement Markov chains for sequences of notes that we play. But for today, it's really just concentrating on rhythm. So for this, we're going to use the ML star package from the Max Package Manager. So let me just bring that up here. There's Flucoma, by the way, which, oh no, that's Fluid Audible Edge. There's fluid corpus manipulation. So that is also where a lot of the objects I'm using are coming from. But here's ML star. So this is a great library, lots of useful stuff in it. But I will just be using the one of the objects, which is ml.markov. And so I want for my first Markov object to use make a third order Markov chain. So it'll take into account the last 3 entries to create the probability tables. Now, what I want to do is get the time differences between the onsets and have that be the data that I train my Markov chain with. So the idea is that this will spit out, well, inter-onset timings, or i.e. rhythmic timings, that will give sort of a similar feel to the audio corpus that was used to train the data. So this may or may not be useful depending on what your audio corpus is, but I think it's a great place to start. Again, just like we were talking about last video, the idea for rhythm at this stage is just to get a kind of a smorgasbord of possibilities that we can then draw from. Okay, so I'm going to build this by first getting the onset timings. So for this, we need a fluid.buff to list. We want to set a super high max size. The default, I think, is 256, so you got to be careful about that. And of course, the source is going to be our onsets, which we can see on screen here. I've already calculated, and there's a total of 590 onsets that were found in this particular audio corpus. That will send it out as a list, so we want to iterate that list using that object there. From there, I want to have my data in milliseconds, and the onsets are stored in samples. So we'll need samps to milliseconds here. And then because this is a tilde audio object, it will give a signal out of the left. So from the right, we'll get our data integers, or rather floats. However, I don't want to, I want to sort of round things off a little bit so that, you know, for instance, if the audio corpus plays something that is 500 samples long, or let's say 5,000 milliseconds long, and then another note that's 5,003 milliseconds long, I wanted to basically treat that as the same rhythmic duration. So I'm just going to round to 20 milliseconds as sort of close enough, because I think that will lead to a better result from our Markov chain. Okay, so we're rounding that number. Now we can use a bucket to sort of pass the numbers sequentially. There are different ways that one can do this stage, but for whatever reason, this is how I did it for my planning. So trigger bang bang, oops, float here, and we'll want 2 float objects here. One of the floats will be stored here, the other float will be stored here, and then we also need to bang them out in this order. So this will just make sure the numbers are coming out in the correct order into our subtraction here. Oops. Yeah. Oh, and I also want to, because I won't be giving all of the numbers as a list directly, I want to make this dynamic as well. So it will sort of add to the list or add to the table as it goes. Okay, so this will basically, this will give the ml.markov object the information that it needs, but before it can actually generate or draw from the probabilities, you need to send it a build message. So I'll create that here. And we'll also, upon new training, not because it's dynamic, we won't just want to add to it infinitely probably. We probably want to have one corpus be the training and not more, say if we like deleted it and put in a new corpus or whatnot. So we want to have reset to clear the data. We'll also want to be able to clear out the bucket so that we don't get a first value that is incorrect. So we'll just need an order of operations here. That should work. So we'll want to first clear the bucket and reset the Markov. We'll second want to give the Markov object data, and third we'll want to build the Markov object. Now if we send a bang here, it should just do it. I'm going to print the output here so that we can see it, see if it worked properly. All right, so let's go for it. Oops, I got that annoying bug where it turns that into unclickable. Okay, so I figured out the bug I had in here. It was just that my float box here was also in the left inlet. It's always some silly little thing like that. Okay, I'll move that back over here. Okay, so let's test this again. So we have our print still in action there. And now let's train it. Great. So we have these much smaller values and they are not all repeating. So there's a lot that are the minimum slice length, which is why we're getting such small values. But in any case, we'll now have millisecond time differences between notes that are banged out of the ml.markov object that are similar to the training onsets that were detected. So if we want to test this out, then all we need to do is send bangs at these time differences to the trigger. And so I have this R tester here that that we'll use to hit the KD tree of the grid there. So we could just do something like, well, we could use a counter to do it, or we could make a simple gen object to do it. I think I'll do it in gen. So with gen, all we should need is, and a counter, which is counting by 1, and we give the number that comes out of ML Markov as the max count, and we could have just the count come out as a sanity check, as a debugging check, but then the flag can be the signal for our to bang out the next number. So from here we'll want, actually we include in here, we can go the ms to samps, like so. And now we will want to have a trigger to turn this on and off. And we can use a gate here. Put a bang that we can see our trigger. We'll want to put the output of this to it. Why do I have 2 inputs? Ah, yes. In 1. So from ML Markov, we'll get our max number from there into the gen. And then the right inlet is the flag, so that will need to be converted, into a bang using edge. And then that will be gated. Great, and we'll also want to have, we'll probably want to bang when we turn it on. Yeah, so we'll want an initial bang, so we can do select 1 for turning it on, and then it will be open after that to get the one that comes 300 milliseconds or however many milliseconds later. Now this bang will have to go back to here so that we get the next one at that point. Okay, so, and also the initial one by using the select 1 object. So let's see if that works. Great. Okay, so if we send this to tester, we should hear some, oh, of course, I can't just send a bang to tester. I need to send it XY coordinates. So let's just use this simple, make this simple patch again, where we get random XY coordinates between 0 and 1. Random. I should just save this so that I don't have to rebuild it every time, but in any case, it'll just take a second. Divide by 100. Both of these, and then join, not John, but join them together like so. And cool. Now, to make it more convincing, we probably want to change exactly how we are playing it back. Maybe changing the window shape, maybe actually elongating the amount of audio that we sample so that things kind of combine more smoothly and not just bop, 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 sort of where the window is so clearly articulated. But we'll leave that for another video. We have it sort of functioning at least the way we want. All right, so there is training our Markov from, or a Markov chain from the detected onsets. Now I'd like to be able to train a Markov chain that is from the live input, sort of like one that's ever evolving, or that could be sort of reset and retrained on the fly. So that should actually be fairly simple. So if we receive our onset here, so this is the onset detection that is in this p onset settings subfolder. Yeah, we see it's getting our onsets. Now we'll want off the bat to have a gate so that we can add to the training, and we can again, or I shouldn't say again, but we can use this timer object like that. Let's also, there we go. Let's also round to 20 milliseconds. And let's filter out super long. Yeah, let's filter out super long durations between onsets. So, and I don't just want to clip it, I just want to remove them entirely. So if I'll use an if object. So if the first input, or the integer coming in the first input is greater than, let's say 10 seconds, then, or sorry, is less than 10 seconds. So I'm going to accept it, right? So if $integer1 is less than 10 seconds, then we send it out. Okay, so anything larger than 10 seconds. We also set a minimum in a similar way. And then we just want to send that to another one of these ml.markov objects, and it will train it dynamically as it goes. I'm going to create a bang for later. Now, it will need to get the build message in order to actually create the chain. So for that, I think we don't want it to build on every single onset. Maybe we could do it so it builds on every 10 onsets. So let's do a counter that counts to 10. And we can do select 9 because it counts 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And like so. And that can also come out of the, oh, actually come out of here. Yeah. Okay. So, yeah, let's see if it works. So if I just talk for a little while, it will get onsets. Or it should be working already. I'm going to keep training it, but I'll see if it's just working already if I send it. Yep. Great. Okay, so I'll stop training it now. And likewise, we could send, we could hook it up to this thing that we built down here to send it to the tester. But yeah, so now we have one that can be created dynamically. We probably also want a reset so that we can choose if we want to continue adding to it or if we want to get do a fresh training. So that could be, you know, that could just, we could have like a receive, reset live Markov, and then we could send that a bang if we want to. Train it fresh rather than adding more values to the Markov chain. Okay, so that's it for the Markov objects. So let's close that up. So now let's get another subpatcher, and this can be our pulse, pulse detection. And we can start with kind of the simplest form of pulse detection using our onsets. So we'll receive onset again here. Bop, 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 great. And hold on, I just want to double check how I was doing it here. Okay, yeah. Okay, so we can start with our most basic form of this. If we just get the times between our onsets, and then we can use ZL stream to then create a stream of X number of of times in a list, and then get the median of that list. Great. So ZL stream going straight to ZL median, and then in the right inlet here, we'll give it how many of the inter onset times we want to take into account. So I'll just let's do 10. Why not? And now to get it to BPM, we want to do our conversion. That is now quite familiar to us of 60,000. And I'll do it as a float because for BPM, we might as well. Yeah, so let's get our float box, and we should already be getting, yeah, great. So if I give a really even, clear thing like is locking into our BPM there. So one issue with this is it kind of jumps all over the place even when there is no pulse. So we want some way to see, just it's sort of how confident we are that there is in fact a pulse happening. Rather than it just be sort of random values and then this is kind of a meaningless thing. So we can do that by comparing. So this is just for pulse, really, like even pulses. Subdivisions will sort of not be really taken into account here. But what we can do is take our most recent inter-onset time difference, and we can compare it to the current detected pulse, right? The median of the last 10. Let's make it an absolute float value. And so now we'll have this number. So this is this is sort of how far away, how clear, if it's a 0, it's basically the onset difference is exactly the same between what the last onset difference was and the median over the last 10. So if I give it a really even thing, that number should be lower. So it's got a bit of a lag, but you could see that once I did about 10 clicks, that was quite a low number. So what we could do is we could convert this into a kind of a confidence of if there's a pulse or not. So I would scale this. If the difference in BPM is 100, I'd say it's basically 0 chance of it being really clearly a pulse. So we'll scale 100 to 0 to be between 0 and 1. So we'll be very confident at 1 because that is exactly the same difference. And at 0, we will have not a lot of confidence at all that there is a pulse that's happening. Yeah, so if it's just me talking, oh, yeah, right. So I also want to clip it because, of course, sometimes the difference is going to be much larger than 100. So I'll clip the output to be between 0 and 1. So if it's a negative number, it just becomes 0. Yeah, okay, great. And in fact, we could potentially run into problems if this is not an absolute number as well. So I'm going to do that again. There we go. Okay, great. So yeah, not a lot of confidence here. Well, occasionally I guess you get lucky, but in general, not a lot of confidence. We might want to smooth this number out. You know, we could do the same thing here where we take into account, you know, maybe some smaller number like the last 4. And then we'll get our smooth confidence. Yeah, so it's gonna hopefully stay pretty low. I think my onset detection is really sensitive. which means that I'm just getting a lot of like minimum threshold. So I'm going to change my onset detection to 0.2. Yeah, okay. So now it's not so trigger happy, and this should work better. I mean, all of these things that we're building onto this are kind of dependent on accurate onset detection. If it's not accurate, then we're not getting good data to do the calculations with. Okay, yeah. So it seems a bit better now that the detection's better. Okay, so I'll give it a very clear even pulse, and we'll see if the confidence goes up. So again, there's a bit of a lag for it to get up there, and then a lag for it to go back down, but it is working. I'm going to move on to a much more advanced patch that is not created by me, but was created by Philippe Salambier. I hope I'm pronouncing their name correctly. Yeah, Philippe Salambier. And they have a BPM detection that they designed for piano music, but is a pretty interesting patch that I find to give you pretty musically relevant meter and pulse information. So yeah, this is the creator of this patch here, and I've maybe changed a couple of minor things, but really it's all around the edges, it's really their patch. They've posted it on the Flucoma discussion boards. So that's the root of this, and he was nice enough to give me permission to include it in this project in this video. So what they're doing here, I'll just go through it quickly, is they're using fluid onset feature to keep track of the making sort of a graph or a histogram of the onset features of the input coming in. And then they're writing that to a buffer. And then they are computing BPM by looking at the peaks in that buffer. So this is the sort of the heart of the calculation here. So first they find the peaks using this bit of code here, looping through some of the indexes of the buffer. Then they interpolate that data, and then they look at the sort of the evenness of the time differences between the peaks in the between the peaks within that buffer. And then they compute how confident they are, and then they wrap the value so that the BPM is always between 30 and 360. So we could change this if we don't want to have such a high BPM or such a low. Maybe we would want to wrap it between 40 and 200 or 40 and 250 or something like that. But I'll leave it as in this way for now. So yeah, quite an advanced bit of programming in the Gen code box that is used to compute all of this. And again, using the Flucoma objects to sort of power the data collection. Okay, so we see down here, we have our BPM, the variance in BPM, and the confidence, which is updated based on how often it's getting onset. So I already have it hooked up to our onset detection here. And it only updates when the intertime difference, I think, is under a certain threshold. Great. So we can sort of hear the accuracy of this if we want by using by setting it to a metro and hearing it as clicks. So if I do that now, that's me talking apparently is at 273 BPM, which is interesting. But if I give it a bunch of clicks, it will eventually move to whatever speed that I'm doing. So let me just try to train it now. So what's kind of cool there is that I can then start playing off of that beat, and it won't. It will still hold the pulse behind it. So yeah, so this is quite powerful. I will integrate this into the patch as well. Okay, so that concludes all of the things that I wanted to put into the patch today. And I think next video we will probably try to upgrade how we're sampling from our corpus, try to get more sort of musical possibilities there, and then it will be combining the rhythmic and the sampling things that we've built so far together to actually be able to generate sound. And then after that, it will be experimenting with a bunch of different behaviors and trying to make it a musical and interesting AI that will interact. So we probably still have quite a few videos left, to be honest, but we are hopefully soon going to be able to get to something that we can actually at least play a bit of music with, even if in a bit of a limited way. Okay, so that's it for today. Thanks.